So we discussed titration curves and deprotonation, dissociation of glycine, which has just 2 ionizable functional groups. But for some amino acids, there is an ionizable side chain. Let's look at histidine as an example of such amino acid. So histidine has an imidazole group in its side chain. So we'll start with the mostly protonated form. So we'll draw alpha carbon, protonated carboxyl group, and here is our side chain, protonated imidazole group. And of course, that charge is delocalized between those 2 nitrogen atoms. So that's our most predominant form at very acidic conditions. It has a charge of +2 or 2+, right? 2+. Now, we start adding a base, a strong base, and the first group to lose its proton will be this carboxyl group, because the pKa of that carboxyl group is 1.8. So after we have a pH, above the pKa of 1.8, the predominant form will start to be that form in which we still have protonated amino group, we still have protonated side chain, but our carboxyl group will be deprotonated. Now, the next group to be, and of course the charge here would be +1, 1+. If we start to add in more of the strong base, then the next group to be deprotonated would be this side chain, because the pKa of this group is 6, right? 6. Now, the conjugate base of that second dissociation step would be this neutral form of histidine, in which both the side chain and carboxyl group are deprotonated. So that is that sweeter ion or neutral form. And we can even go further, right? Deprotonate histidine even further, because it still has that amino group that is still protonated. The pKa for that group is 9.2. So if we have a pH of the solution higher than that, the predominant form of histidine would start to be that fully deprotonated form with a net charge of -1. 1-. So now let's sketch a titration curve for histidine and determine its isoelectric point, the point at which the neutral form, which is right here, is maximized. So we are going to have dependence of pH on the amount of or equivalence of a strong base added. You cannot see it right here, so I'll put it right here. Okay, so remember, when we reach this half point or midpoint, we are we start with that fully protonated form, right? With this charge of 2+, and we start having this form dissociated into this conjugate base, because we are looking just at this equilibrium for now. So those two forms, the acid and the conjugate base, have equal concentration when pH is equal to pKa. So we need to plot it somewhere here, right? So that happens at half sodium hydroxide added. So after that, when we pass one equivalent, we have our 1 plus form predominate, and that continues until our pH reaches the pKa of the side chain. So at that, and this happens at 1.5 equivalents added. At that, we have plus 1 form and neutral form present at equal concentrations. And finally, if our pH is higher than the pKa of the side chain, we start having this last third dissociation step to be significant in terms of which of the form predominates. And again, where if we just look at this equilibrium, another midpoint when we add 2.5 equivalents would be achieved when pH is equal to pKa, right? So that is when the concentrations of those two forms, the neutral form and the form with a charge of 1 minus, are equal. And that happens at the pH of 9.2. So yeah, that's my 2.5 equivalents, right? So here we have 0 charge. Here we have 1 minus charge. So now let's connect those equivalence points. Remember, we need to have like low slope or around the plus minus to the pKa, right? So we can position it like that, right? And of course, we are sketching, so we may not be precise. And then the slope is high when we are outside of those buffering ranges. So that would be our titration curve for histidine. Now, which pKa's do we need to average in order for us to determine the PI, the isoelectric point of histidine? So don't forget the definition of the PI. So PI is the pH at which the neutral form, which is right here, is maximized. And as you can see, this neutral form is maximized then something in between of those two forms, right? You need to already deprotonate the side chain, but you still need to have the amino group protonated, right? And that happens at the pH equal to the average between those two pKa's, because that corresponds to our neutral form. So the PI for histidine will be 6 plus 9.2 over 2, which is it's 15.2, 7.6, right? So that's the PI. And as you can see here, our 7.6 indeed corresponds to the maximum amount of our neutral form of histidine.